Let's build a parallel plate capacitor in its simplest form. Imagine two flat conducting plates suspended in a vacuum, separated by a tiny sliver of space. Right now, they're neutral. Hooking these plates to a battery pumps in opposite charges. The inner surfaces shimmer, transforming them into a storage device. To understand how this device works, we only need to look at two physical dimensions. The first is area, which we'll call capital A. For our model, we assume the distance between the plates is much smaller than the dimensions of the plates themselves. That brings us to our second variable, separation, or lowercase d. The ratio between the surface area and this gap determines exactly how much energy the system can hold. But why would a device's electrical storage limits depend entirely on these physical dimensions, rather than the raw electricity flowing into it? This equation shows the core ratio of electrostatics. Capacitance, C, is defined as the total charge Q divided by the potential difference V. The standard SI unit for this property is the farad, named after Michael Faraday. To see the scale of a single farad, consider a capacitor with a 1 centimeter gap. To reach a capacitance of 1 farad, those plates would have to be 30 kilometers long. Because a single farad is so large, real-world electronics operate in tiny fractions of the unit. They use microfarads, they use nanofarads, and even picofarads. Each plate generates its own electric field based on its surface charge density, or sigma. Sigma is the total charge divided by the area of the plate. In this schematic, vector arrows emerge from the positive plate and dive directly toward the negative one. Notice the regions outside the plates. Above the top plate and below the bottom plate, the fields from the positive and negative surfaces point in opposite directions. This creates a mathematical cancellation. In these outer regions, the total field strength equals 0. In the inner gap, however, the fields from both plates point in the same direction. Instead of canceling, they add together. This results in a uniform electric field, strength sigma divided by epsilon naught, trapped entirely between the plates. Because this field is uniform, the potential difference, or the work done in moving a charge across the gap, is simply the field strength multiplied by the distance. We can now substitute our field definition into the equation for potential. V equals E times D becomes charge times distance divided by area and the permittivity of the vacuum. This expression links the potential difference directly to the physical dimensions of the plates and the properties of the vacuum. We have the variables required to test if the total charge, Q, actually influences the device's inherent storage capacity. To find the final answer, we plug our new geometric definition for V back into the master capacitance formula, C equals Q over V. When we divide these terms, the charge variable, Q, appears in both the numerator and the denominator. It cancels out completely. This leaves us with the final formula for a parallel plate capacitor in a vacuum. The physical consequences are direct. If you double the area, you double the capacitance. If you double the distance between the plates, you cut the capacitance in half. The math confirms the thesis. Capacitance is a purely geometric property determined by the shape, size, and separation of the conductors. Our model of a perfect uniform field assumes the plates are infinitely large. In the real world, plates have boundaries. Near the edges, the field lines bow outward into the surrounding space, a phenomenon known as the fringing of the field. We can ignore this effect in most circuit designs. As long as the gap D is much smaller than the plates themselves, the error is negligible. The ultimate function of a capacitor is to confine electric energy within a predictable region of space, creating a stable, reliable component for any circuit.